Hi students, welcome to Preliminary Chemistry and the Water video series. Excuse me. This is number 8 and is the first of 2 that I'm going to look at involving interactions with water. Now, interactions with water is about solubility. What sort of stuff dissolves in water? And we've already looked at the fact that the polarity of the water molecule is a really important property because it accounts for many of the physical properties that we notice for water, such as its relatively high melting and boiling points for molecules of a similar size, its high surface tension, and also its relatively high viscosity. But the polarity of water can also help us to explain solubility and why certain substances do dissolve in water and why others don't. And of course, the key here is to remember that like dissolves like. That's one of our key rules when we're looking at solubility. And we need to keep that in mind as we go further along, because now we're trying to explain why like dissolves like. So the first thing, and probably the easiest one to identify, is the ionic compounds. Now, most ionic compounds, like sodium chloride, are soluble in water. Not all of them are, and there are going to be some exceptions we're going to look at a little bit later on in a couple of videos' time. But most ionic compounds are soluble in water, and that's because each of the individual crystals is a network of alternating positive and negative ions. And if we just draw a couple of these as a starting point, then what we notice is that the positively charged region of the water molecule is going to interact with the negatively charged region of the ionic substance. So in this case, the water molecules are able to rotate and set themselves up in such a way that their slightly positive region is going to interact with the negative ions in the ionic substance, and they're actually going to be sufficient in order to pull that away. So the chlorine will be attracted to the positive part of the water molecule, and of course then other water molecules may surround it, completely removing it from the network from which it originated, and as a consequence of that, the crystal will slowly be broken down. Of course, the same thing is going to happen to the positive ions as well. So if we've got sodium ions exposed in our crystal, all that will happen is the water molecules will rotate. So now it will be the negatively charged, slightly negatively charged oxygen region of the water molecule that will be interacting with our cation, with our sodium ion, and it'll drag it away. And again, the same sort of thing will happen, just in the reverse, where the negative regions of the water molecules are attracting the positive region or the positive ion of sodium and taking it away from the crystal structure. And again, this is how the substance will be dissolving in water. As I mentioned, not all ionic substances are soluble in water, and there are some rules around that, which we'll have a look at a little bit later on. But effectively, how we know or how we explain this effect is that the electrostatic attraction, which is just the attraction between negative and positively charged objects, is going to be stronger or weaker than the electrostatic attraction to the water molecules. So if there are two oppositely charged particles and then another one comes along that is opposite, then there's going to be a force of attraction here and a force of attraction here. Logic suggests that whichever is the bigger force wins the tug of war. So if the water molecule, if this is the water molecule, comes in and this is a chloride ion and this is a sodium ion, then if this is a bigger force, then it will drag the chlorine away. Of course, all of these don't act in isolation, and you have lots of water molecules and a lattice, a crystal lattice of sodium and chloride ions, but this is the explanation for why this occurs. We also want to have a quick look at soluble molecular compounds. Now, the like dissolves like is probably less obvious for something like ionic and polar water molecules, but it's still based on the fact that there is two opposite charges interacting with each other and attracting with each other. But certainly from our like dissolves like, we know that polar solutes will dissolve in polar solvents and non-polar solutes will dissolve in non-polar solvents, and that's our like dissolves like rule. So why then do polar substances dissolve in water? Well, the reason they do is because the polar molecules have a dipole, so therefore a negative and a positive region, and of course the water molecule also has the same, so it's going to be attracted. Let's just try that again. So it's going to be attracted to the, it's very hard to think and talk at the same time and draw. And being male, I have trouble with multitasking, but as you can see, so here's going to be an oxygen, hydrogen, hydrogen. This is the positive region over here. You can get off. And these are the negative regions here. So these interactions here are the ones that are critically important. So if we have a polar molecule, then we're going to have some interaction of polarity between these two polar molecules, one surrounding the other, which creates a solution. Now, if we would look at something like a molecular compound which was like sugar, or also something like ethanol, so it doesn't have to be a solid, it can be a liquid, they will dissolve in water because of the interaction. So sucrose molecules are full of OH bonds, and so is something like ethanol. So let's just sort of put ethanol in like this for the time being. The water molecules, so the sucrose are going to be complex molecules. We won't draw disaccharides just for time. But of course the hydrogen, oxygen, hydrogen, these interactions here are the H bonds that are going to be attractive and are going to pull two sucrose apart. And likewise, if we have an ethanol here and a water molecule here, then again you're going to have some hydrogen bond interactions, which are just dipole-dipole interactions between these two molecules. And what they're going to do again is they're going to be pulling them away from a second and subsequent ethanol molecules. So again, it's about the strength of that electrostatic attraction. If the attraction between the water molecule and the regions of the covalent molecule that are dipoles or can potentially create hydrogen bonds is strong enough, then they'll be separated from other molecules that they're being held to. If it isn't, they won't, and they won't dissolve. I think we might leave it there, and we might have a look at some other interactions between substances and water in the next video. Thanks for watching.